and my supervisor is Professor Sushobhan Samanto. I am presenting my topic, which is machine learning based state of charge estimation for lithium ion battery pack. So today I will discuss about the basic overview on battery management system, then electrical equivalent circuit models, then lithium ion cell testing, and then parameter estimation of the equivalent circuit model, then SOC estimation methods, and then SOC estimation by OCB SOC method,
Just
and Coulomb counting method, then SOC estimation by random forest algorithm. And what we are estimating, someone has unmuted. So I think Namairakkam is on. Yeah, thank you.
You please carry on, Sourabh. I am muting.
Okay. And then battery parameter monitoring using Bluetooth module. Then I will conclude. So first, we have to know how many types of battery are available in the market. So batteries are broadly categorized based on the chemical material used in in them. So these materials determine the battery's energy density, lifespan, cost, and the specific application. So figure 1 shows the different type of battery. So first is lead acid battery. It is the one of the oldest and most widely used battery, and which is also used in automotive application. So why it is used widely used because of its inexpensive and robust, and it has a lower energy density compared the other lithium-ion batteries. That's why it is not using in the EV application. Then nickel cadmium batteries. So it is known for their ability to handle a large number of charge discharge cycle, and as it has more lifespan, so it can be used in EV application. But what is the problem is that it is suffering from the memory effect. Means where their capacity is reduced when it is not fully discharged before the charging. And another problem is the cadmium. So as cadmium is present in this battery, so it is not useful, means it is not good for the environment. It is also nowadays it is not using in the EV. Then nickel metal hydride battery. It is the improvement of the nickel cadmium, and it offers higher energy density and are more environment friendly. So it is used in hybrid vehicles and consumer electronics gadgets. Then the lithium ion battery. So lithium ion battery are mostly used in the EV application because it has the higher energy density, longer life, and relatively it has low weight. So the lithium-ion battery can be branches into the multiple chemistry, which are the lithium nickel manganese, lithium iron phosphate, lithium cobalt oxide, lithium uh, uh, lithium nickel cobalt aluminum oxide, and then lithium manganese oxide and lithium titanate. So lithium nickel manganese cobalt oxide, it is used in the EV and laptops also, because it gives the balance between energy density, and it is also safe. And then lithium cobalt oxide has also high energy density but limited cycle life. It has less than 1,000 cycle lifespan, so it is only it has the stability, so that's why it is used in smartphone basically. Then nickel cobalt aluminum oxide, it also offers high energy density and long lifespan, and it is used in Tesla vehicle, but same problem here also cobalt is there. That's why Tesla is right now not using this type of battery. So they are going for the lithium iron phosphate battery. Um, then lithium manganese oxide, it also provides a high energy density and high means better thermal stability and safety. So it is used in the power tools and that medical devices. And then lithium titanate battery. So it is a safe battery, fast charging can be done and highly durable. And it is used in the high power application. So what is basically used nowadays in EV applications is the lithium iron phosphate. As lithium iron phosphate battery has a better thermal stability, long life cycle, and it is safer, but it has slightly lower energy density. So this is the overview of on the different type of batteries. Now, what we can see in the figure 2, that uh, uh, we can plot the volumetric energy density with the specific energy density. So what is volumetric energy density? So volumetric energy density is the watt hour per liter, means in 1 liter area how much watt hour can be taken from the battery. And what is energy density, specific energy density is the per kg, what will be the energy density of the battery. So if we increase the specific energy density, then it will be lighter weight. And if the volumetric energy density is higher, then it will be means the size of the battery can be less. So what we can see that in the left side, the um, lead acid battery is positioned at the lower left corner with low energy density, indicating they are heavy and bulky compared to their energy storage capacity. Then nickel cadmium is there. Then nickel metal hydride battery is there. Then lithium ion battery comes. So it has the highest specific energy density with volumetric energy density is there. Then polymer lithium ion battery, it is also have the it has highest the specific energy density, weight is lower, but now it is not used in the EV applications. So So lithium-ion battery, here we can tell that lithium-ion battery can dominate due to its higher energy density, where lithium-ion metals are not using due to the battery performance of the battery performance. So in the figure 3, one demo battery pack is there. What we have used in the um, lab. So, what are the advantages of lithium-ion battery? LiFePO4, because it will take the action in the EV application in the near future. So it has the longer life cycle, then safety and stability, and then environment friendly and low self discharge, quick charging and low maintenance is required. So, what are the disadvantages of the lithium-ion battery? So, voltage, current, and temperature should be in safe operating region. Means if we overcharge or over discharge the battery, or if we charge the battery after the its C rate, means if we discharge, means if in the data sheet it is clearly written that in which current rate we can charge or discharge the battery, and if we exceed that limit, then it can damage the battery. Then temperature is also a concern, because if the temperature is increases beyond the safe operating region, then thermal runaway can be occurred. Their protection is required for the lithium-ion battery. Then aging effect. If we what is aging effect? Means whenever we are charging or discharging the battery with increasing the charging or discharging cycle, the capacity of the battery can be decreased. So the battery deteriorates with the cycle. So this is the aging effect. And then deep discharge, what I have discussed in the first point. So that's why there is a battery management system is required to protect the battery and to uh, observe or monitor the battery at every instant. So that's why battery management system is required. So what is the battery management system? So battery management system is that which can monitor and the protect the battery or battery pack. So the first function is the data acquisition. What is data acquisition? So BMS gathers data from various sensors embedded with the battery pack, such as voltage, current, and temperature sensor. So the data is processed to assess the battery's current status and performance. And these collected data helps the battery management system monitors essential parameter like SOC and whatever the parameters, means the resistance. So SOC, SOH, all the parameters we can monitor in the real time. So the second is the state monitoring. What is state monitoring? It involves the state of charge, state of health, state of power, then state of energy. These type of states battery management system can monitor by accurately determining these states. The BMS ensures that battery operates within the safety operating region and delivers the required performance. And then cell balancing. In large battery pack composed of multiple cells, where there may be the variation in the battery voltage and capacity, because due to as in the manufacturing time there may be slight difference in the battery manufacturing. That's why there may changes in voltage and capacity also. So cell balancing ensures that all the cells have same voltage, uh, same voltage and capacity, so that it can charge and discharge uniformly. This improves the overall efficiency and cycle life of the battery. So it can prevent the issue like overcharging or discharging, over discharging in the itself, uh, and which can damage or which can means lead to the premature aging or safety hazards. Then another function is the safety and protection. So one of the most critical function of the BMS is to ensure the safe operating of the battery. So it provides the overcharge, over voltage, under voltage, then over current, over temperature protection. So the system continuously monitor these parameters and can uh, mm, uh, initiate the protective measures, like it can cools down, means for cooling down the uh, um, battery, and the fan can be on, or there may be the passive and active temperature control is there. So like that, so that the to prevent to dangerous condition like thermal runaway, or it may get otherwise it may get fired. So then the thermal management system. So batteries are highly sensitive to the temperature changes, and excessive heat can degrade their performance or even cause safety risks. So the thermal management system regulates the temperature of the battery pack, either through the passive cooling or the active cooling method. And what is passive cooling method? It is like heat sink, heat sink, and then active cooling method is like fans or a liquid cooling system, which is widely used in EV applications. So this is essential to prevent overheating, which can lead to reduce the efficiency or uh, efficiency. So what we have seen for the Ola electric scooty also, there was some problem in battery management system. So there was the thermal runaway of the scooty. So then energy management system. So the battery management system manages the energy flow between the battery and the device it powers. So so that it can ensure the optimal performance. It controls the charging and discharging rate, maximizing battery efficiency and lifespan. So this function is very crucial because of to estimate the range of the uh, EV, then and optimizing the energy used based on the driving condition. So all of these functions ensure that the battery operate safely, efficiently, and reliably. And the battery management system is essential for maximizing the battery life while preventing failures that can lead to system damage. So these are the things what I have discussed. So battery management system is manages the rechargeable battery, such as it monitor, balance, and the protect the batteries. So it can measure, monitor the voltage, current, temperature. Then for computational cases, it can estimate the SOC, SOH, SOP, and SOE basically. Then as all the cells are not of same SOC, that's why cell balancing is required, and which can be done by the battery management system. Then to protect the battery from over voltage, over current, over temperature, or under voltage, uh, um, means deep discharge. This can be protected by this battery management system, and all the parameters can be uh, means can be measured and can be noted down using the data acquisition, and it can be displayed also, and all the communication with the means battery to the device can be done by the canvas system. So now I will discuss about the uh, SOC estimation process as one of the major critical role of the battery management system is to estimate the state of charge estimation. So, what is state of charge? So, it is a percent means remaining capacity of the battery to the rated capacity. What we can see in the figure 5 that when it is 100, so in the battery, if we see that there is a inactive portion is there. So if a lithium-ion battery has nominal voltage of uh, 3.6 volt, and if the maximum voltage is 4.2 volt, and we can see that the minimum voltage is 2.8 volt. So this is the inactive portion to 0 to 2.8 volt. So after that 2.8 volt to 4.2 volt is the 0 to 100% SOC, and generally 0.0 to 20% and 95 to 100% to charge the battery. This means more time is required. I will explain later this one. So the the formula of the SOC is SOC dot equal to minus uh, um, eta I by Qn, where I is the discharging current, and the Qn is the rated capacity. So why this SOC is required? So SOC is required to estimating the running distance. Means in electrical means in EVs. So knowing the SOC helps predict how much distance or usage time is left before recharging is required. For example, in EV, so if we drive, then driver can plan the when we have to charge again. So second is the to avoid the overcharge and over discharge of the cell. Charging a battery beyond its capacity, then temperature will rise, and due to overheating, it may damage the or there may be risks of fire uh, in the battery. So deep discharging also cause the permanent damage of the battery, because there is a crack in the electrodes. That's why it may not use further for charging or discharging the battery. So it will reduce the lifespan of the battery. So SOC helps means SOC estimation helps the battery management system ensure that the battery operates within the safe operating region. Then the cell balancing. So if what I have discussed, that due to manufacturing defects or due to the transportation, the cell voltages or capacity may not match for each cell. If the cell voltages are not same for each all the cells, then obviously the SOC of the individual cell of the battery pack cannot be same. So um, SOC can help the battery using the battery management system. And if we observe if we monitor the SOC, it can ensure the cell balancing. Uh, and since cells in a uh, pack can have slightly different capacity and discharge rate. BMS uses the SOC data to balance the cell and preventing from the overcharge and over discharge, and it will improve the pack's overall efficiency and life cycle. Then uh, due to this cell balancing, we can ensure that battery pack can be effectively used. So, if we effectively use the battery pack, then the weight of the battery pack also can be reduced, because it is also a concern for the EV application. So before going to the battery SOC estimation, we have to know about the battery modeling. How can we model a battery? Because these after doing the battery modeling, and the parameters of the battery models can be used for the SOC estimation process. So now I will discuss about the battery modeling method. So first model is the empirical model. So empirical model are built from the experimental data without necessarily considering the internal physical processes of the battery. So these models used the regression model, then curve fitting technique to relate the battery input to output. So if we so we can measure of only measurable things of the battery are the current, load current and terminal voltage. And using that current and terminal voltage, we can estimate the SOC and SOE. So NARST model and the Shepherd model are the very well-known methods of the empirical modeling. But due to the lack of accuracy under different conditions, it is not used in the um, now. Nowadays, it is not used. Then electrical equivalent circuit model. So electrical equivalent circuit model simulate a battery using standard electrical component like resistor, capacitor, and voltage source. And it is widely used for the SOC state estimation of the battery. So there are we can see that there are three types of generally three types of ECM models are there. So RINT model, random model, and NRC model. So these models RINT model is basically the one voltage source and one internal resistance in series. At the first stage of the battery research, we have used that RINT model, but due to it cannot explain the sluggish response of the battery during the pulse test. That's why RINT model is not used. Uh, Randall's model also cannot explain the diffusion effect of the battery. That's why it is not used. Then NRC model comes, and NRC models means it can be 1RC to NRC model. So 1RC model add one parallel RC circuit, uh, accounting for the dynamic voltage response. Uh, so so 2 RC model is the it consists of 2 RC circuit, and it can both capture the short term and long term dynamic behavior, and it can be add multiple RC circuit to improve the accuracy of means accuracy of the response, means voltage response. So there are so with the increasing the order of the model, we can get the accurate model, but the complexity will also increase. So to trade off between the to balance the trade off between this complexity and accuracy, 1RC and 2RC models are mostly used in EV applications. So then electrochemical impedance models are there. So this model is based on the analysis of batteries impedance over a range of frequencies. So it provides the uh, internal electrochemical processes by representing the battery as an impedance network useful for diagnosis of battery aging and performance issues. So then electrochemical model are also mainly physics based model. It can simulate the electrochemical processes in the battery. So here intercalation methods are used to see the model, to design the model, and the microscopic and macroscopic view of the electrodes and the electrolytes are used in this model. So Euler-Fuller Newman model is very much well-known method for electrochemical model, which uses the partial differential equation to describe the battery behavior. But these models are computationally intensive. That's why it is used only in the research, and in real-time application, it is mainly not used due to the complexity. And then the data-driven models are there. So these models use the machine learning uh, techniques to predict the battery behavior based on the historical data rather than the underlying the physical principle. As so if we have big data, then we can use the data-driven model. So there are some techniques are of data-driven models are neural network, fuzzy logic, decision trees, Gaussian processes, and then support vector machine. So what is neural network? It can approximate complex relationship in the battery behavior. So it is also useful for the SOC and SOH estimation. Then fuzzy logic, it is very popular technique, data-driven technique. So it can handle the uncertainty and imprecision, and so it is, and this makes it useful in modeling the nonlinear battery system. Then decision tree, so it is a simpler machine learning model that can make the prediction based on the rules extracted from the data. And what I have used and what I will explain in the next slides, that random forest algorithm is also one type of the decision tree technique. Then support vector machine. So it is also good for the classification problem, like distinguishing between healthy and faulty battery states. So then the support vector machine is there, and this is also a model which can capture that uncertainty in the battery. So these models can be useful in real-time battery management system due to their predictive power and the adaptability to the new data. So again, before going to the SOC estimation techniques, we have to know, or we have to discuss about the electrical equivalent circuit model, because these the parameters of the electrical equivalent circuit model is used for the SOC estimation technique. So, before going to the electrical equivalent circuit model, we have to know about the polarization of the battery. Then, so what is polarization? So, polarization is the uh, voltage difference that occurs due to the internal resistance and electrochemical processes when a battery is the in under load. So, so it leads to a lower terminal voltage compared to the OCB. That's why the in under load condition, the terminal voltage is not same as the OCB. For polarization is of two types. One is static polarization. Another is the dynamic polarization. So static polarization is caused by the ohmic resistance, so representing the immediate voltage drop due to the battery's internal resistance when a load is applied. So this is constant and does not vary with time, as it primarily accounts for resistance in the electrolyte, electrode, and the connector. So, what is dynamic polarization? So, it is a time dependent, and it results a sluggish electrochemical processes, and it can be splitted into two components. So, one is the activation polarization, another is the concentration polarization. So, activation polarization is linked to the resistance and capacitance that that the electrons encounter while overcoming the activation energy barriers during charge transfer reaction. So it causes the rapid voltage changes over the short time intervals. And then the concentration polarization, which is the modeled with the resistance and capacitance. It is also a parallel RC circuit, and it is due to the concentration gradients in the electrolyte and electrode, which affects the voltage on a longer time scale. So this slower process leads to the gradual recovery of the terminal voltage toward the OCB after the load is removed, as the system returns to the equilibrium. So here we can see that this is a 1RC, figure 8 is the 1RC model, and figure 9 is the 2RC model. So in figure 8, it consists of the one voltage source, one internal resistance, and one RC parallel circuit. So the drop of the voltage drop due to the internal resistance and RC is called the polarized voltage. And in the 2RC means in figure 9, the voltage drop due to the internal resistance and two um, RC parallel circuit is called the polarized voltage, and these voltage, the UPA UPA is the activation polarized voltage, and UPC is the concentration polarized voltage. And the output and the state equations are uh, shown in the slide. So this is the experimental setup for the battery testing, and by these tested data, we can estimate the parameter of the equivalent circuit model. So this is basically a Arvin instrument. So these Arvin instrument is used for the to test the Samsung 26J 18650 cell characteristics. So the pink color cell is this Samsung battery, and Arbin Mix Pro software is used for monitoring and control the cell, which we can say in the which we can see in the figure 10. So what Meets Pro supports the real-time viewing, plotting, and exporting the battery test result to the CSV file, and it communicate with the battery management system via the CAN bus to prevent the overcharging and deep discharging. So control signal and real-time test results are managed via the Ethernet cable, which from the host computer. The cell has been here in this experiment. The cell has been tested at 0.52 ampere for constant charging, and minus 0.52 ampere during the discharging. And the current level is low, as we have the limitation, and the voltage limit of this Arvin instrument is that 0 to 5 volt only, and the current limit is 1 ampere. So we can collect the data, then there is the conversion, then we have to clean some data, and then means pre-processing the data is required. Then this is the experimental result. If we do the pulse test, then we can get the this type of terminal voltage profile. Samsung 26J battery has the minimum voltage of 2.8 volt and the maximum voltage of 4.2 volt, and it is 2.6 ampere hour battery. So if we zoomed this terminal voltage for an instant, then we can get this type of figure. So figure 3 explains the Varnasi model, means battery response. And if we do using that 1RC model, then we can estimate the parameters of the 1RC model using this response. Where we have discussed that static polarization is the instantaneous voltage drop of the battery. So, if we know the current difference of the pulse, then we can calculate the R naught or internal resistance of the battery. And if we do the steady state analysis, then we can get the value of the RTH and CTH. If we so the um, final time or settling time or time required for the fully charge fully discharge the capacity, that will be the 5 RTH CTH, and the voltage difference during that pulse, that will be the R naught plus RTH into del I. From these two equations, we can get the capacitor means active concentration. Sorry. so activation capacitance of the cell. So then comes to the figure 14. So here, if we explain the 2RC model, then we know that there are two types of polarization is there. One is activation polarization, and another is the concentration polarization. So ohmic loss is same for these two models. Then activation polarization is due to the one RC parallel circuit, and concentration polarization is the other RC parallel circuit. So there are two time constants are there, and the lower time constant is due to that activation polarization, and the higher time constant is due to the concentration polarization. So what we can see that we cannot estimate or directly tell about the parameters of the battery. So we have to estimate using different techniques. Uh, so where in this here I am using the least square estimation method for to estimate the parameter of the 1RC model. So if we can see that what I have told here, that the polarization voltage is due to the R naught and these parallel RC circuit. So GS will be the impedance voltage drop by current. So it can be written like this. And if we using the bilinear transfer rule, then the discrete transfer function will be like this. So equation 2 represents the discrete transfer function of impedance impedance. Then this transfer function can be represented by the equation 3, and if we compare this equation 2 and equation 3, then we can get the A1, A2, A3 value. So but our main goal is to estimate the parameter of the cells, means are not RTH and CTH. So what we can do, so we can write this equation 1 and equation 3, means from that equation 1 and equation 3, so EL by IL equal to EOC minus U OC minus UL by IZ. And from here, if we know that temperature and SOC of the battery are very slow with time. That's why if there is a small change, then there is a small change in the SOC and temperature as well. So we can approximate that UOC equal to UOC K equal to UOC K minus 1. So these equation number 4 again can be written as equation number 5, and here we can see the terminal voltage at instant k equal to 1 minus A1 into UOC, means OCB voltage at instant k, plus A1 into terminal voltage at instant k minus 1, plus A2 IL A2 into IL at instant k, plus A3 into load current at instant k minus 1. So in the right hand side, we can see there are some known parameters, and there are some unknown parameters are there. What are the known parameters? Known parameters are the terminal voltage and load current, which can be measured using the sensor. So we can discriminate this known values and the unknown parameter values. So if we consider the parameter vector theta is a unknown parameter value, then it will be the terminal voltage equal to the known parameter into unknown parameter. So the known parameter is the observation data matrix, which is psi. So phi equal to 1 minus A1 UOC, A1, A2, A3. And USC is we have not measured using the experimental setup. There is a we can measure the open circuit voltage from in the experimental setup also, but it requires so much time because it is a time consuming process. As the terminal open circuit voltage is the no load voltage, that's why when we are giving the pulse and we are measuring that terminal voltage, that will be that will not be the open circuit voltage, as because there is a polarization drop. That's why it should means we have to give time to take rest the cell up to the when that cell will come to the equilibrium state. After that only we can take the terminal voltage value, which will be the OCB value. So for every pulse, after giving every pulse, we have to take rest for 2 to 3 hours. After that, we can take the terminal voltage value, and this is due to this time-consuming process. We want to estimate the open circuit voltage also with these unknown parameters. So this is the that theta is the unknown parameter vector, and psi is the known parameter vector. Where what we can see that terminal voltage that depends on the terminal voltage and load current only, and the past time data of that terminal voltage and load current. So, so equation 5 can be expressed in the matrix form. What is that? UL equal to psi into theta plus epsilon. So epsilon is the error vector, and we want to minimize this error vector. So that the cost function of the least square estimation method is given by the J equal to epsilon transpose into epsilon. And these so to minimize this error, we have to do that del J by del theta, which will be the 0. So the parameter vector of the battery model can be solved as that theta equal to psi transpose psi whole inverse into psi transpose into UL. So here we can see that parameter vector can be represented by the all the known values. So by this equation, we can get the A1, A2, and A2, A3, and OCB value. So again, if we inverse bilinear transform of the GZ, then we can get the GS. So from the GS, we can get the GS in the form of all the unknown parameters that we have estimated using the LSE method. And in the equation 1, we have seen that the GS is represented by the R naught, RTH, and CTH, and GS is represented by the A1, A2, A3. So from there, we can get the value of the R naught, RTH, and CTH. And these will be the estimated parameters of the first order equivalent circuit model. And similarly, we can do for the 2RC model here. We can see that the concentration polarized voltage is included in this 2RC model. The voltage difference is due to the R naught RPA, means this is due to the activation polarization, and this is due to the concentration polarization. And using the again bilinear transfer rule, and again inverse bilinear transfer rule, we can get the are not means all the parameters of the ECM. Then these are the estimated parameter value. So what we can see or what we can observe from this 1RC and 2RC model, that all the parameters are varying with the SOC of the battery. So parameters are not fixed for a one charging or discharging cycle. So these parameters are the change in parameters can be um, analyzed by the differential capacity curve, or if we explain the intercalation process, then we can check or verify or validate that parameters value. So this is the workflow for that SOC estimation process. So first, a pulse test is done in that Arbin battery testing system. So these Arbin battery testing system is collaborate with the host computer, and these data is means one IP port is connect with the host computer to save the experimental data. Then one an electrical equivalent circuit such as 1RC and 2RC circuit was designed in MATLAB, and Simulink and carpeting techniques were used to match the simulation with the test result. So the ECM model parameters like resistance, capacitance, and OCB were estimated using the least square estimation algorithm, with SOC can be expressed as a function of terminal voltage, and SOC can be represented in terms of OCB. So the initial SOC was estimated using the fitted OCB SOC curve, and the battery SOC further calculated during the testing. The workflow included the calculating the accumulated capacity, and the comparing the result from the simulation and experimental platform to ensure the accuracy in the SOC estimation. So now we can explain the SOC estimation methods. So, what are the SOC estimation methods used in that means literature? So, first is the Coulomb counting method. So it is one of the most simple SOC estimation technique, relying on the integrating the current flow into or means which can be delivered or accumulated from the battery over the time. So SOC is calculating by measuring the current, then integrating that measured current, and initial SOC is needed here to accurately estimate the SOC of the battery. But the main disadvantage is due to the sensor noise and integration accuracy, or the accumulative errors may come due to the noise. So to accurately estimate the SOC using that Coulomb counting method, one accurately uh, estimated parameters are required for that. So next is the open circuit voltage method. So open circuit voltage method directly estimates the SOC based on the predetermined relationship between the open circuit voltage and SOC. But as I have told that this method requires the battery to rest for a significant times, means 2 to 3 hours at no load condition to reach a stable OCV from which SOC can be determined. So while the OCB method can provide accurate OCB readings, it relies on the relaxation period, makes it unsuitable for the real-time application. This is particularly limiting in the dynamic environment, uh, where batteries are really ideal long enough to measure the OCV. So next is the model-based method. So model-based methods are the uses the mathematical methods, and ECM models are basically used for these type of SOC estimation methods. This method can be very accurate and responsive to dynamic operating condition, but its performance depends heavily on the accuracy of the battery modeling and requires detailed knowledge of the battery parameters. So these model-based methods are very complex and require computational resources for real-time application. Then it comes to they are also of two types. One is the adaptive filter based. So in the adaptive filter based, there are like Kalman filter family and other families. So Kalman filter family means that Kalman filter, extended Kalman filter, uncentered Kalman filter can be used for this SOC estimation. Other filters means that recursive least square estimation methods, and like the recursive methods can be used for the SOC estimation. And nonlinear observers for sliding mode observer and other methods, nonlinear methods can be used for this SOC estimation. Then machine learning methods are there. So again, the machine learning methods mean neural network, fuzzy logic, decision tree, and Gaussian process and support vector method can be used. These employ that advanced algorithms to predict the SOC. So these models are trained based on the historical battery data. Then learn complex relationship between the input variable and the output variable. So here, in our case, input variables are the voltage, terminal voltage, and load current, and the output parameter is the state of charge. So machine learning methods can explain, means it can get the adaptability and can handle that complex nonlinear behavior that are difficult to model using the other methods. But the main disadvantage is this requires the extensive training data and significant computational power that makes them more suited for application where this data is available and processing power is not a constant for that application. One of the most popular method is the Coulomb counting method. So it is a current-based estimation technique. So these current using that load current, the charging and discharging in current can be integrated with time to measure the capacity of the battery. So the relationship is shown SOC equal to SOC naught minus 1 by Qn. So 0 to T I into dt. So I is the discharging current. So positive I is the discharging current, and SOC not is the initial SOC, and QN is the nominal capacity. So several factors that affect the accuracy of this model, including that temperature variation, the battery usage history, and that cycle life. So errors can accumulate due to that sensor inaccuracy or varying operating condition. So additionally, determining the initial SOC is crucial here, as errors in the starting point can lead to a large inaccuracy over time. So the initial SOC is often obtained using the OCV SOC curve, where the battery open circuit voltage correlates with its SOC after a resting time. So this is basically means figure 17 is basically a block diagram for that Coulomb counting method, where I've shown that the if the battery is connected to a load, then we can measure the current using the current sensor, and that current can be used for the SOC estimation method, and the SOC curve is used for that to modify the conventional Coulomb counting method to accurately estimate the SOC of the battery. So figure 18 shows the estimated terminal voltage of 1RC and 2RC, um, 1RC and 2RC model, and the that red one is the measured terminal voltage, and blue one is the estimated 1RC terminal voltage, and orange one is the estimated 2RC terminal voltage. And figure 9 shows the error between these two curves. Means if we compare the estimated terminal voltage with the measured terminal voltage, then we can see, means I have got this type of error, and which varies between 0.4 volt to minus 0.4 volt. And if we estimate the SOC using this Coulomb counting method, then these SO means estimated SOC curve I got. So the advantages are these are the very easy to implement and cost effective. And disadvantages of Coulomb counting method is only applicable when initial state of charge is known, and the error in sensor current measurement increases with the time due to the integration. So first disadvantage is the when initial state of charge is known, then only we can implement this one. Otherwise, what happen that if we start the car, and it will always if it always shows from the 100%, then there is a massive error in the SOC estimation process. So we have to first estimate the initial SOC, then we have to eh, um, calculate the integration of the current. So this is the flowchart of the SOC estimation method. So first, we have to the process begins by the monitoring the terminal battery terminal voltage and load current. Then we have to check whether these load current is zero or not. If it is true, then battery is not under the load. If after that, if IL is zero, then the terminal voltage is measured and the SOC is determined based on the OCB SOC curve. And these SOC value is saved for the further calculation. Then if IL is not zero, then the algorithm checks whether IL is greater than zero or not. If it is greater than zero, then it indicates that a charging is required. Otherwise, it moves to the discharging mode. So in the discharging mode, the system checks whether the terminal voltage is greater than 2.8 volt or not. If it is greater than 2.8 volt, then it calculates the charge released and update the SOC accordingly. If terminal voltage drops below 2.8 volt, then the battery is considered as the exhausted state and it switches to the charging mode to recharge the battery. So when the battery is in the charging mode, then it checks if the whether the battery is fully charged or not, and if not, then if not fully charged, then it continues to accumulate charge again. So once the battery is fully charged, the system records the battery state and switches to the discharging mode. So in both the charging and discharging mode, the uh, algorithm calculates the SOC based on the accumulated charge or released charge using the Coulomb counting method. After each that charging or discharging cycle, the SOC is updated and monitored so that the accurate estimation of the SOC can be done. Then, now the function of battery management system is to monitor the SOC for each instant of the battery charging or discharging. So this is the flowchart. Then what I have discussed in that previous slide, that initial SOC estimation is required to accurately estimate the uh, battery state of charge. So open circuit voltage is basically a voltage based SOC estimation method where the relationship between the battery state of charge and its OCB is used to predict the SOC under different loading condition. The OCB SOC curve is typically determined offline by fitting experimental OCB data to a mathematical model. uh, what I have used in the using the least square estimation method. So, but here some approximation is there because it is not included the effect of the diffusion voltage and the hysteresis effect. So, diffusion voltage, what we have discussed in the polarization slide. So this method ignores the diffusion voltage caused by its electron concentration gradient within the battery, which can affect the accuracy of the SOC estimation process. So what is uh, hysteresis. Hysteresis is when OCV can differ depending on whether the battery is being charged or discharged, leading to the inaccurate SOC prediction. So while charging, we can see that the terminal voltage is greater than the open circuit voltage, and while discharging, then that open circuit voltage is greater than the terminal voltage. And if we do the test in a cycle, means if we charge and then again discharge the cell, then we can see that there is a gap between that uh, um, terminal voltages. So this is called the hysteresis effect of the cell. So figure 22 is the estimated OCV of the 1RC and 2RC. Towards the models. So figure 23 is shown the SOC versus OCB curve for towards the model, and here we can see that this is highly nonlinear function, and if we highly nonlinear function, okay, and we can express by a polynomial equation, which I will discuss in the next slide. So figure 24 is the OCV, is a 3D plot between OCV, load current, and terminal voltage, and we can directly estimate the OCV using this polynomial equation. So if we know the if we write the OCV in function of that terminal voltage and IL, and if we know the value of UL and IL, then we can get the OCV value. So here we can see that OCB can be represented by this polynomial equation, and root mean square is like 0.117, and we can write these SOC in terms of OCV like the second equation, and root mean square is that 0.0134 314. So while the OCB SOC curve of lithium-ion batteries is largely stable, it varies depends on the charging discharging rate, battery temperature, cell variance, and battery cycle life, and other factors. So what are the advantages? So when the accuracy of SOC estimation can be compromised by using lookup table of OCB SOC directly, SOC can be predicted by the OCB value. So if we want, if we if accuracy is not required, then we can directly measure or estimate that SOC using the SOC OCB curve only. So what we have seen that this is a, non-linear equation, and with the time these equations also is changed, and in some microcontrollers higher order polynomials cannot be used. So to increase the accuracy of the estimation method, we can use the piecewise linear SOC OCV curve. So if we use like this, and if we segmented all the means these curve, this figure 23 curve, then we can get this piecewise linear SOC OCV curve, which can give better accuracy for SOC estimation. So this is the now we come. So what we have discussed about the Coulomb counting method, and we get the SOC value corresponding to the time sample. So now we will discuss about the SOC estimation in the using the random forest algorithm. So for that, what we have to means 2 is discussed here. Okay, first, what we will do is that we will there is are two parts. So one is offline process and another is the online process. In offline process, we have done first we have measured the initial voltage and load current. Using that initial voltage and load current, the least square estimation method, we have got that OCV value, and using the Coulomb counting method, we got the value of the SOC for each instant. So from using that OCV and SOC data, we can get that SOC OCV curve, and the using the load current and the terminal voltage, we can uh, train a model which is to enhance the SOC estimation. So here we have used the Coulomb counting method for that modeling. So we make a model which is a trained model, which we can from which we can estimate the SOC. So these model and that SOC OCV card, what we put in the dump in the ESP32 microcontroller, and there while we are measuring the load current and terminal voltage, and these model, we can get the SOC, and we can monitor using the HC05 Bluetooth module, and so we can monitor the real-time data in the system host computer. So why means what are the usefulness of the RFR algorithm, means random forest regression algorithm for SOC estimation? So it can handle the nonlinearity. As we can see that OCV and SOC is a highly nonlinear curve. We have to take some algorithms which can uh, capture the complex nonlinear relationship between the battery parameters and SOC, and then reduce the overfitting. In the next slide, we will discuss that how random forest algorithm reduce this overfitting. So robust with the missing data. So it can handle the missing or noisy data effectively, which is useful when working with the real-time battery dataset that may have gap or measurement errors. Then it incites important features like identify the parameters, the voltage, current, temperature are most critical for the SOC estimation. Then high accuracy and generalization. It also offers the high accuracy across a wide variety of battery types and operating conditions also, by generalizing well to unseen data, unlike support vector machines, which may require extensive tuning. And scalability is another useful features of random forest algorithm. So it is suitable for large data set due to the parallel processing of decision trees, making it ideal for handling the vast amount of battery test data required for accurate SOC prediction. So this is the flowchart for that SOC estimation process in the ESP32. What we have to do that first we have a battery pack. Then we have to do that data acquisition. So it will collect the raw data from the sensor. Uh, um, um, voltage, terminal voltage, and load current. Then data pre-processing should be there. So data in the pre-processing, there are two types of things we have to do. One is data resampling and data normalization. What is data processing? It cleans the data to handle the missing value or noise, and converting categorically into uh, um, numerical format. Then data resampling is required. So there may be case means there may be some data is there which don't have the consecutive sample data, means like uh, um, if we collect the data like 1, 2, 3, 4 sample times, but maybe there is a case where we get the data one, then three, like that. So there is a missing data of sample number two. So we have to adjust the frequency of the data by changing the time interval, and to ensure that there should be a uniformity in the data set. And this may involve the techniques like interpolation or extrapolation. So then data normalization should be there. So these scaling the data to a specific range to ensure all the features contribute equally to the model training process. So we know that in the during data normalization, we consider that the data should be in between of 0 to 1. So all the parameters value like terminal voltage is 2.8 to 4.2. So this should be normalized to 0 to 1, and load current may be anything. So it also can should be normalized to 0 to 1 value only. Then training data. These now we have normalized all the data. Now we have to train the model. So the subset of data used to train the model, enabling that the algorithm to learn the pattern and the relationship between all the parameters. Generally 70, it's up to the user. So generally what I have used, that 70% of the data has been used for the training data, and then the testing data. So testing data is used, the final subset used to evaluate the model performance, providing an unbiased assessment of its predictive capabilities. Is 20% of the data has been used for the test data, and then remaining 10% data has been used to validate that validation. So these data used to tune the model parameters and prevent that overfitting, ensuring that the model generalizes well. Then we are going to the random forest regression. So these builds the multiple decision tree and merges them to obtain a more and accurate stable prediction. And so we have the data of terminal voltage, current, and these input data. Using these input data, we will get the output like SOC. So now we have to build a model. By selecting features, choosing in the model architecture, and hyperparameter configuration is there. So after building the model, we have to train that model. So in the model training, the selected algorithms learns from the training data, adjusting its internal parameters based on the input data. So after training the model, we have to check whether this the strain data has the error, means root mean square error uh, is the we have to check. So what is that error? Error between that predicted and the observed values, and we have means referenced one tolerance value, and if it is exceeded, then it means it should be less than the tolerance value. If it exceeds, then again the model has to train. Then what I have discussed, it is written here only. So this is the random forest algorithm. So in the random forest algorithm, so what we have seen that we have a data set D. This D contains the battery parameter. Uh, like the terminal voltage and load current SOC, and it is structured as a matrix with the dimension of M cross N, where M is represented by M represents the number of samples, and N denotes the number of features. To improve the model performance, bootstrap sampling is applied to the D. What it results in the creation of the multiple data sets like D dot, D double dot, like DTN. So each subset contains slightly different samples, allowing for the training of the distinct decision tree. So each of these subset is used to train the individual decision tree. Each tree learns to predict the SOC based on the provided battery parameters. So DT1, DT is the decision tree. So DT1 to DTN are the decision trees are here. So once the training is completed, each decision tree generate a SOC prediction and represented as the M1, M2, like to MN. So these prediction vary slightly due to the differences in the training data from the bootstraps sample. So this is the output of each individual decision tree. So after getting the output of each decision tree, the final SOC estimation is derived by averaging these decisions from all the decision tree, which helps to improve the accuracy of the SOC estimation by minimizing the variation across the individual trees. And it is it gives the robust SOC estimated SOC value. So what are the advantages of random forest algorithm? It combines the multiple weak learners, means decision trees, to improve the accuracy level. So it reduces the overfitting. Why? Because it averages all the output of the decision tree. So overfitting can be reduced by this method and enhances the generalization. So robust with the missing or noisy data, as we have done the pre-processing process. So it is this structure makes it easier to explain how the random forest operates while showing its key steps visually through the flowchart. So, so this is the decision tree. What we have discussed in the previous slide, that DT is the decision tree, and there are n number of decision trees are there. DT1 to DTN. So, what we have seen, there are five steps are there, as we have selected that there are five steps are there. Each so we can say that each rectangular shape is a node. So each rectangular node represented a split based on the features. So like x naught, x1, and the features are the terminal voltage and load current, like that, which appears to be comparing values of different features in the data set. And if like what is the zoomed version, x2 less than equal to 0.23, and the value of in each node shows the prediction at that point of the tree, and the number of samples that reach the node is also indicated. So what is squared error? So the squared error mentioned in each node indicates the error, means the difference between the predicted and actual value at that split. And lower squared error value is means shows the better prediction at that node. So then sample count. So sample count is the each node shows the number of samples passing through it, which helps understand how the data is divided at each decision point. And then the here we have to see that whether the decisions are true or false. If it is false, means we will check that x2 less than equal to 0.3, 0.23 or not. If it is true, then it will go to the left side, and it is false, then it will go to the right side. Like that, the decision can be taken. Now, this is the ESP evaluation board. What I have used in that to dump the code. So first, what I have done, I have used that Google Colab for the coding, and there using the Python, we can write the random forest algorithm and all the modeling part. Then we can dump that code in the ESP32, and here mm, in the diagram, what we have seen that we have to measure the data. Then these then terminal voltage and current, load current data can be collected through the GPIO pin, means that analog signal pin, and we can um, mm, estimate the SOC of the battery. So then after the estimation, we want to that um, mm, monitor the SOC of the all the parameters of the battery actually. So the parameters like terminal voltage, load current, and SOC, battery SOC. So what we can see that the transmit receive data pin is required, and power supply and ground is required. So that VC's power supply can be taken from, and then this transmit data pin is connected to these RX pin, and this TX pin is connected to the AC05 RX pin. So why these Bluetooth module is required? As Because these it is a mm, because in real time application we want to monitor these parameter value, battery parameter value in our Android phone. So what we can do, that we can transmit the data from the microcontroller to our means Android phone. So this Bluetooth module is a means it is easy to implement. That's why we have used this Bluetooth module, and uh, then these hardware implementation. Oh, sorry, it is written in Arduino, but it is ESP30. Oh, sorry. Mm, it is wrongly written in the heading that it is hardware implementation using Arduino. So where in figure 31, we can see that SOC estimation has been done using Coulomb counting method, and that random forest algorithm for a 12-volt lithium iron phosphate battery pack, by 3P configured battery pack using the ESP32. So here we can see the battery is connected through a MCB. MCB is required in discharging case. They are may not required, but in the charging purpose, if we not use the MCB, then the charger or the DC supply can act as a load. Then battery will discharge through that electronic through the load, and if that load do not have any protection, then the DC supply may damage. That's why MCB is required. Then the voltage and current sensor. Here I have used the LEM 25 P LEM LV25P is for that voltage sensing, and LA25P is for the current sensing of the for the current sensing of the battery pack. And I have not discussed this principle, Hall effect sensors principle, working principle, because yesterday Manos Ranjan Jena has completed that part excellently. That's why I have not discussed this part. Then SAMPS board is required to power up all the sensors here, and then ESP32, we get all the voltage and current signals to the ESP32, and we can monitor that voltage and current signal in the host computer. And these ESP32 is used to monitor uh, means to power up this Bluetooth module AC05, and these data will go to the means our Android phone. So this is the result. The figure number 32A is the it shows that simulated and experimental estimated SOC results which we got here, and we have seen that the initial SOC is approximately 80%, less than 80%. So it is not starting from the 100%, 100%. As we have accurately estimate the initial SOC of the battery. So in the 32B, what we are seeing that the left side, leftmost side result is the what we can monitor in the system or host computer. Then the middle one is the zoomed version of the Android phone data, and the last picture is the screenshot of the Android phone. And we can see that it actually transmit the data to Android phone accurately. There is no problem. The RMSE values are the 0.583%, 0.426%, and 0.385% respectively. While the estimated SOC has been compared with the simulated SOC by modified Coulomb counting. So modified Coulomb counting means that conventional Coulomb counting with the SOC OCV curve. Then experimental SOC by modified Coulomb counting method, and then estimated SOC by random forest algorithm, what we have done in the experiment. So the MAE means the mean absolute error is the 0.112%, 0.095%, and 0.085% respectively. So these are the some result which we got from these experiments. This was done for the constant current load, means using the resistive load actually, and this is done by varying the knob of the barrier. So we can get this type of load current. So this is a dynamic load current, and we can get these 33B SOC. And this is the estimated SOC, and simulated SOC has been compared, and see depict the error of that estimation. And then 34 is the estimated SOC for constant current. And so if we do using constant current, then this type of estimated SOC we can get. Then uh, we what we have done that in previous cases, that SOC OCB curve has been done for the ambient temperature in the previous cases, but now we have got some result for constant temperature cases. So we have tested the battery for 5 temperatures, so like 20 degree, 0 degree, 10 degree, a 15 degree, and minus 20 degree centigrade. So what we have seen that open circuit voltage changes with the changing of the temperature. What we can see is that if we increase the if we decrease the temperature, and we come to the negative temperature, then there is a huge difference between the open circuit voltage. So for let we take the 3.511 volt open circuit voltage, and we can see for different temperatures, like in 20 degree centigrade, it is like approximately 20%, and these 3.5 for minus 20 degree centigrade, it is like 76.82 percentage. So there is a huge misestimation of the SOC in the means open circuit voltage in the of the battery. So that's why the lithium-ion battery should be no, operate in the safe operating region like 0 to 60 degree because in India also if the temperature is high basically that's why if we go beyond that temperature then there will be they may damage or they may reduce the lifespan of the battery. And similarly, if we see for single SOC, then we can see also that there are difference in for like say it is a 18.24 percent. Then we can see the open circuit voltage for different temperatures are different. So we have seen this observation. Then after that we have done SOC for different estimate the SOC for different temperatures also. So here we can see with increasing the temperature, the it will take more means for discharging the cell it will take more time to discharge. So the estimation for different temperature. Then now conclusion. So here what we have discussed is that 1RC and 2RC models are analyzed and parameters are estimated by linear sorry least square estimation method. Then estimated parameters are validated by terminal voltage of the physical battery. So means the tested data using the turbine instrument. Then polarization effect results in the terminal voltage difference between first order and second order model, as 2RC model can explain the concentration polarization effect. And then open circuit voltage is estimated by the least square method using the experimental data. What the other researcher do using that experimental method. So SOC is estimated here by Coulomb counting method by integrating the charging or discharging current, and initial SOC is estimated by SOC OCV curve to modify the estimation process. And then the SOC estimation process combines offline algorithms like RLS method and then Coulomb counting and the machine learning method also with online real-time monitoring using ESP32 microcontroller and Bluetooth device that HC05. And then random forest regression method and regression algorithm and modified Coulomb counting improve the SOC accuracy by averaging the predictions from multiple decision tree trained on the battery data. And the system is validated with a dynamic load test showing minimal error. Means RMSE is 0.00176% and efficient computational 0.1166 second per sample. So these are the references what I have referred in my literature. Thank you.
Thank you, Sourabh, for your very nice presentation. Lot of things you have covered. I hope participants will get a lot of information from you. So thank you for your valuable time. So I'm asking or requesting the participants if they are having any queries, please discuss over here. Okay, so please raise your hand or you can directly ask to us.
Sir. Hello.
Hello, sir.
Yes, sir. Yes, sir.
Very good morning, sir. I'm Chansekar here from BMKB Engineering College, Salem.
Okay.
So, I would like to apply the battery same like And can we able to connect while flying the drone with the solar panel?
Sorry, you want to apply the battery in the robot?
No, drone. While drone is flying,
Oh,
so
okay.
that
So
will be
yeah.
like discharging condition. At the same time, can we add a small solar panel to make it charge? So two-way process, charging
Yeah,
and
but
discharging.
the solar panel will give the more weight, and that I don't know that drone will sustain with that means weight or not.
The small
It is
solar
applicable,
panel,
no
sir, which
problem.
gives 1 ampere current, 5 watt till.
Okay. We
Like
can
how
definitely
much we are connected, same size.
how we can connect.
Like battery we are mounting on the top, sir, near GPS on the center of the drone. So
Okay.
it is a lithium battery, like charging, discharging batteries. So
Okay.
in that we have one cable connectors through which we are charging as a normal AC supply. Same we can connect with in the sunlight mode. So solar will give the energy to the battery. So may know any impact will come in the heat energies. While getting drain again, it's same simultaneously getting charged.
Which type of battery you are using?
Lithium battery cell.
Means lithium. Which type of lithium battery? Means there are so many types of lithium batteries. What I have discussed in my slides, right?
Like you
So
have shown
if
in slide,
that
no same battery I have.
okay, so if the temperature of the battery will increase in direct sunlight, means you are not using the direct sunlight, right? It is covered, no? The battery is covered by something.
Battery will be in covered mode.
Yeah. Then I think there is no problem. So I
So
have to
no
check
any
that one.
heat impact will come for drone.
Sorry.
Like my battery is lithium-ion battery, 4300 milliampere. It's covering with 3.7 volt. So 3 battery I've connected in series.
Okay.
For the same, I would like to connect with solar panel while flying mode because its cost is too high. Like 15,000, 20,000 coming. It's running only for 10 minutes while flying mode, sir. While carrying with 1 kg weight. So if give the solar panel means it will receive 3.5 to 7 volt. So while parallelly it will charge and it can go for half an hour even in sunlight mode flames.
You
So
can use that solar panel also, no problem.
okay, thank you, sir.
Excuse me, sir.
Yeah.
Sir, am I audible, sir?
Yeah.
Firstly, thank you so much, sir, for such wonderful and insightful presentation. Sir, actually, I want to ask, sir, as you means your work on basis on the random forest or machine learning based, sir, as you mentioned that other model-based approaches like Kalman filter, extended Kalman filter, like particle filters, but they are very computationally means they are very computationally intensive algorithms. In case of
Yeah.
random forest and your SVM, they are data driven. So, sir, this is also gives a good real-time estimate because also you have to train and validate. Then they have to deal with lots of data at the time, and they are also computationally intensive. Means as means in compared to particle filters and extended Kalman filters, they are just means making a prediction and estimation. And this random forest and other machine learning based algorithms, they are also dealing with the data. But how we can implement such algorithms in case of real time BMS? So means nowadays is it feasible in means right now in electric vehicles to implement such a intensive, computationally intensive algorithms in real time, give this real time estimates. Thank you, sir.
So you want to know about that how we can use Kalman filters or particle filters in real-time application, right?
Yes, like extended Kalman filter and unextended Kalman filter are not such computationally intensive as your particle filter and machine learning based algorithms. So for current electric vehicle scenario, we can implement such algorithms to give real-time estimates electric
Yeah, we can
vehicles.
use definitely. There is no problem. I have also used Kalman filter, extended Kalman filter in my system. So there are lots of hazards are there to implement that coding in the microcontroller, but we can do. There is no problem. But what you have to do that you have to take relevant microcontroller for that. Means if we use a low cost microcontroller or means low memory microcontroller, then there is a problem of memory. So what you have to do, you cannot store the data. You have to what you have to means while you are collecting the data or measuring the data, then if you have done work on the Kalman filter or extensive Kalman filter, then you know that there is some covariance matrix and all you have to calculate for each instance. So you have to do only for that instant only. Then you have to take result and store outside of that one, so that you can easily do whole the process. And if you want to store all the data for all the instant, then there will be problem, and then you may get the memory effect that the store is full like that. Okay. So in real time also there is no problem to implement these algorithms.
This is the main benefit of this algorithms because in case of model based, there we have to estimate covariance matrices. But in case of random forest and other machine learning based, we don't need to means do such mathematical means formulation. Means this is the main I think means
And the main advantage of that model based is that you don't require any condition. Means in machine learning methods, what you have to take that you should have the big data. Means you have to train the model for all the conditions, and if your battery will come under different condition, then the battery will not give you the exact or accurate SOC value. In model-based system, there is no condition, means environmental condition or other conditions. It will get result. It will take the data from the battery, and accordingly, it will predict the SOC. And this is the main advantage of model-based system. But in that machine learning method, if you can give all the condition data, means all the battery data for all the conditions, and the battery is working or operating in that conditions only, then it will be the perfect. And another one disadvantage of machine learning method is that if you don't have the data, means if you have less data, then also it will give you the uh, means not inaccurate results. It may give because it will not it will give the interpolated or extrapolated data. Then it will be the approximated data only. So this is the problem for this machine learning.
we can use in a hybrid mode, sir. No? Means both the machine learning as well as the model base. If we use in a hybrid
Yeah,
mode, then
you can use, no problem. But you have to these will be more complex because first thing, that model based system is computationally so complex are there, complexity are there. Again, you are doing in machine learning, so the when you are writing the code for these machine learning, then it will be very much problematic because there are that in model-based system, there are so many mathematics are there. So first we have to know about the how to implement that mathematical things in machine learning. Then only we can do these things.
Thank you so much, sir, and thank you for sharing your results. Thank you, sir.
Thank you. Okay, thank you.
Thank you, Sourabh. I hope there is no other query from the participants. So again, I'm thanking you for your deliberations. Okay, it's really nice and very informative, as well as there are a lot of results for better understanding. Lot of algorithms you have discussed over here, how to implement, and lot of things you have covered. I hope that participants, as well as we are also getting lot of informations for regarding the implementations of BMS in our real-time systems for different applications. Thank you, Sourabh, for giving us your valuable time, and thank you all.
Thank you, sir.
Thank you. So now yes. So now we will go to our next session. Okay, so